Close your eyes if they aren't already closed. Take one slow breath in and let it go. There is nothing you need to solve right now. Nothing you need to hold together. Tonight, the only thing being asked of you is something very simple: to lie here for a while and allow the quiet to slowly find you. And as the day begins to loosen its grip on your shoulders, your jaw, the small muscles behind your eyes, I want to explore something with you. Something remarkable that is happening inside your body right now, whether you notice it or not. Your brain is listening. It is scanning the room. It is measuring the sounds around you. It is checking the temperature of the air, the rhythm of your breathing, the tension in your muscles. And very slowly, very quietly, it is asking a single question: is it safe enough to sleep? For some people, the answer comes almost instantly. Their bodies relax, their breathing slows, and sleep arrives gently, almost anywhere. On a plane, in a car, in a room they have never seen before. But for others, the brain hesitates. Even in a quiet, comfortable room, something inside remains alert, listening, watching, waiting. Tonight, we are going to explore why. We are going to move gently into the biology of feeling safe. What safety means to the nervous system, why some brains learn it easily, why others take longer, and how the story of your own life quietly shapes the way your body decides whether it is time to rest. Because the permission to sleep is not a simple switch. It is one of the most carefully protected decisions the human brain can make. And once you understand how that decision is made, the mystery of why some people can sleep anywhere and others cannot begins to unfold in a very beautiful way. So let's begin slowly. The way sleep itself begins. At the edges, there is a part of you that never fully rests. Even in the deepest, most dreamless sleep, some ancient portion of your nervous system stays softly alert. It listens to the sounds around you. It monitors your breathing. It holds one thread of awareness to the world outside your body, ready to pull you back to consciousness if something changes, if something shifts, if something doesn't feel right. This is not a flaw. This is survival. This is a feature so old it predates language and cities and fire by millions of years. It is the reason our ancestors survived the night. And it is the reason that sleep, for us, has never been as simple as just lying down and closing our eyes. To sleep deeply and well, the brain must first be convinced that the world is safe. Not just that the world seems fine, not just that nothing appears to be wrong, but that the ancient, watchful part of the nervous system has genuinely released its grip, that it has received enough evidence, enough reassurance, to stop scanning and start resting. And that is where things get beautifully complicated, because the bar for safe is not the same for everyone, not even close. Think about the last time you watched someone fall asleep in what seemed like an impossible situation. Maybe it was on a crowded airplane, noise and vibration all around, strangers pressing in from both sides, and this person beside you just went under, tipped their head back, closed their eyes, and within minutes, they were breathing slow and deep, completely gone. And maybe you sat there wide awake, every small noise and shift of air making you more alert, wondering what on earth this person had that you didn't. The answer, at its deepest level, lives in a small almond-shaped cluster of neurons buried in the middle of your brain. And it has a name that may already sound familiar. It is called the amygdala. The amygdala is one of the oldest structures in the human brain, and one of the most tireless. It does not take days off. It does not clock out. From the moment you are born until the last breath you ever draw, the amygdala is running its quiet surveillance program, processing information about the world around you, comparing what it finds against its long library of learned associations, and making a determination that is simple but vital. Is this safe, or is this a threat? It does this faster than conscious thought. Long before you could put words to a feeling of unease, your amygdala has already fired. Your heart rate has already edged slightly upward. The muscles along the back of your neck have already taken on a barely perceptible tension. The decision has been made before you even know a decision needed making. Neuroscientists sometimes describe the amygdala as the brain's alarm system, and that is a useful image. Imagine a sophisticated alarm, one that doesn't just respond to obvious sirens and smoke, but has been calibrated over years to notice subtle things. A particular kind of silence, a certain quality of darkness, a smell that once, long ago, was associated with something painful or frightening. The amygdala holds all of those calibrations, and it uses them every second of every day and, importantly, every night. Now, for most of us in ordinary waking life, the amygdala operates in the background, doing its work quietly, not causing too much disruption. We move through safe environments and the alarm stays low. It notices things, it checks things, and then it settles back down. But when we lie down to sleep, something interesting happens. In some people, the amygdala begins to quiet itself as darkness falls and the body begins its preparation for rest. The world has narrowed to a room, to a bed, to the familiar sounds of wherever home is. The alarm reads the situation, finds nothing threatening, and begins to lower its vigil. The brain can slide towards sleep almost without resistance. In other people, and this may be you, and if it is, please hear this gently. This is not a character flaw. The amygdala does not quiet so easily. It has been trained through years of experience and sometimes through much harder things than years to stay alert, to keep watching, to treat the act of letting go as its own kind of risk. For these people, lying down to sleep is not the simple surrender it appears from the outside. It is a negotiation, a careful, ongoing negotiation between the part of the mind that is tired and wants rest, and the part of the nervous system that was taught long ago that rest without vigilance is dangerous. Understanding why this happens, really understanding it from the inside of the biology, is one of the most compassionate things we can do for ourselves. So let's go a little deeper. The amygdala does not work alone. When it detects something it considers a potential threat, a sound, a smell, a shift in light, an unexpected sensation from inside the body, it sends signals through a cascade of neural connections that affect nearly every major system in the body. It reaches the hypothalamus, a tiny but extraordinarily powerful structure that sits just below the thalamus and acts as the brain's master regulator of bodily state. The hypothalamus, upon receiving the amygdala's alarm signal, sends its own message down the chain to the pituitary gland, and from there to the adrenal glands, those small triangular structures that sit perched on top of each kidney like little hats. And the adrenal glands release cortisol. Cortisol. You have probably heard this word before, usually in a context that makes it sound like an enemy. But cortisol is not an enemy. It is a tool. And under ordinary circumstances, it is an extraordinary one. Cortisol follows a beautiful natural rhythm. It peaks in the early morning, just before and after waking, giving the body the energy and focus it needs to begin the day. And then, over the long arc of the afternoon and evening, it gradually declines. By nighttime, cortisol should be at its lowest point of the entire 24-hour cycle. This low cortisol is one of the essential chemical conditions that allows melatonin to rise, and melatonin is the brain's way of saying, "It is night, it is time, you can rest now." But when the amygdala is running high, when it has learned, through experience, to treat the world as a place that requires constant monitoring, cortisol does not decline gracefully in the evening. It stays elevated, competes with melatonin, keeps the brain in a state of readiness, a state of low-level arousal that makes falling asleep not just difficult but genuinely physiologically uncomfortable. This is not imagination. This is not weakness. This is chemistry. This is the brain executing its instructions with perfect precision, following the program it learned. The question is, who wrote that program? And when? The answer, for many people, begins very early. The nervous system of a young child is extraordinary in its sensitivity and its plasticity, its ability to be shaped and changed by experience. In those early years, the brain is doing something quite specific. It is learning the world. It is building a model of what the world is like, what to expect from other people, whether familiar environments mean safety or uncertainty. And it is calibrating the amygdala's sensitivity based on what it finds. If you grew up in a home that was warm and predictable, where the sounds of the house at night were familiar and unthreatening, where someone would come if you called, where tomorrow was something you could trust, your amygdala had the opportunity to learn a fundamental lesson. Rest is safe. The world continues without your vigilance. You can let go. This learning is not trivial. It is neurological. Research from across the field of developmental neuroscience has shown that early experiences of safety and security quite literally shape the structure and sensitivity of the amygdala, the hippocampus, and the prefrontal cortex. The brain that grows up in safety grows differently on a cellular level than the brain that grows up in uncertainty or fear. Children who experience what researchers call early life stress, which can range from overt abuse or neglect all the way to more subtle forms of emotional unpredictability, chronic family conflict, or simply the experience of having no one reliably available when distress arises. These children show measurable changes in how their stress systems develop. Their hypothalamic pituitary adrenal axis, the very system that governs the cortisol response we just discussed, becomes sensitized. It learns to react more readily, to produce more cortisol in response to smaller stimuli, to stay elevated longer. The amygdala itself may become what neuroscientists call hyperactive, more easily triggered, more likely to flag ambiguous situations as threatening, more resistant to the calming signals that the prefrontal cortex is designed to send down. And this is critical, this prefrontal cortex piece, so let's stay here for just a moment. If the amygdala is the brain's alarm system, the prefrontal cortex is something like the alarm's override switch. The prefrontal cortex, that wide expanse of tissue that sits behind your forehead, is the seat of something that scientists sometimes call executive function, the capacity for rational thought, for context, for the kind of reasoning that can say to the amygdala, "Yes, I heard that sound and I understand why you flagged it, but I've thought about it and it was just the house settling and we can go back to sleep." This communication between the prefrontal cortex and the amygdala is one of the most researched relationships in all of neuroscience. There are direct pathways between these two structures, axons, those long, slender fibers of neurons that carry signals from one part of the brain to another, that allow the prefrontal cortex to send what are essentially calming instructions to the amygdala. It is a top-down regulation, brain science language for the higher brain structures soothing the more ancient ones. In people who sleep easily, this pathway works smoothly. The amygdala raises a flag. The prefrontal cortex evaluates the situation, sends back a reassuring signal, and the amygdala quiets. The whole thing happens quickly, almost effortlessly, below the level of conscious awareness. In people who struggle to feel safe at rest, this pathway is often less efficient. Not broken, not absent, but often undertrained, or sometimes actively competing with a stronger opposing signal. Research has shown that people with insomnia, which is one of the most common expressions of an overactive arousal system, show what scientists describe as a prefrontal amygdala disconnect, where the suppressing, calming signals from the higher brain are not reliably reaching the alarm center below. And this disconnect, this failure of the calming pathway, can have deep roots. It can come from chronic stress, from insufficient sleep itself, from anxiety disorders, from unresolved trauma. It can also, and this is something researchers have found quite consistently, come from a childhood in which the nervous system never had enough consistent, reliable experience of safety to build those calming pathways strongly in the first place. The brain is a learning machine. It builds the circuits it uses most. And for a child whose amygdala was almost always running high, because the environment called for it, because survival made it necessary, the pathways for calming that alarm may never have been thoroughly practiced. The alarm system got strong and fast and very good at its job. The override switch stayed underdeveloped. This is not destiny, but understanding it is the beginning of something important. Let's talk now about the nervous system as a whole, because the story of sleep and safety is bigger than any single brain structure. Your autonomic nervous system, the part of your nervous system that regulates all the processes you don't consciously control, your heart rate, your digestion, the dilation of your pupils, the tension in your smooth muscles, this system has two broad modes of operation. You have almost certainly heard their names. The first is the sympathetic nervous system, which is the system that activates when your brain perceives a threat. This is the source of the fight or flight response. When the sympathetic system activates, your heart beats faster. Your breathing quickens and shallows. Your muscles tense. Blood is rerouted away from digestion and toward your limbs, preparing you to move. Your brain becomes sharper and more focused on immediate threats. Pupils dilate. Sweat glands prepare. Every system in your body shifts into a state of mobilization. This is a magnificent system. It has kept humans alive through 100,000 years of genuine physical danger. When a threat appears, the sympathetic nervous system does exactly what it is supposed to do, and it does it with extraordinary speed and efficiency. The second mode is the parasympathetic nervous system, sometimes called the rest and digest system. When the parasympathetic system is dominant, the heart rate slows. Breathing deepens and steadies. The muscles relax. Blood flows back to the digestive system and the organs of restoration. The body begins the quiet, essential work of repair and renewal. The brain, freed from the high-alert demands of threat detection, can move toward the slower, more diffuse kinds of activity that eventually give way to sleep. For most people, in a typical day, these two systems alternate, shifting back and forth in a dynamic balance. You encounter something stressful, the sympathetic system activates, you move through the situation, the threat passes, and the parasympathetic system takes over, bringing you back to rest. But the crucial word there is takes over, because the parasympathetic system cannot take over until the brain is convinced that the threat is genuinely gone. And if the brain, specifically the amygdala, has learned to treat the world as a place where threats are never fully gone, then the parasympathetic system never gets a clean handoff. The sympathetic system stays active, at least partly, almost always. Even in bed, even in the dark. There is a beautiful, somewhat melancholy phrase that neuroscientists sometimes use: persistent sympathetic tone. It means the background hum of physiological readiness that never quite stops. The body that never quite fully exhales. For people who carry persistent sympathetic tone to bed with them, falling asleep requires not just the absence of activity but the active dismantling of a state the nervous system has been maintaining all day, and sometimes all their lives. Now let's meet the vagus nerve. The vagus nerve is the longest nerve in your autonomic nervous system. Its name comes from the Latin word for wandering, and that name is well earned. This extraordinary nerve wanders from the brainstem down through the neck into the chest, branching into the lungs and the heart, continuing down through the diaphragm into the abdomen, reaching the stomach, the intestines, the liver, the kidneys. The vagus nerve is the primary vehicle of the parasympathetic nervous system. When the vagus nerve is active and well-toned, it acts like a gentle brake on the stress response. It slows the heart, deepens the breath, quiets the gut, and sends a cascading message of calm through essentially every major organ in the body. And one of the most important things the vagus nerve does is carry information in both directions. It does not simply transmit commands from brain to body. About 80% of the fibers in the vagus nerve are afferent fibers, meaning they carry signals upward from body to brain. Your heart is telling your brain something with every beat. Your gut is sending constant reports upward. Your breathing pattern is being read by the brain through the vagus nerve in real time. This is part of why breathing so powerfully affects how we feel. A slow, deep exhale, longer than the inhale, directly stimulates the vagus nerve, sends a wave of parasympathetic activation upward into the brainstem, and begins to quiet the arousal centers. Your heart rate drops slightly, measurably, with each long, slow exhale. The brain receives the signal. The body is settling, and it responds in kind. This bidirectional relationship between body and brain is foundational to understanding why some people can feel safe in their bodies at night and others cannot. It is not just a matter of mindset. It is physiology. The body is constantly broadcasting its state to the brain, and the brain is listening. If the body has learned to hold tension, to breathe shallowly, to keep the heart rate just a little elevated even at rest. If these patterns have become habitual over years, then the signals the brain is receiving are themselves signals of alertness, and the brain responds accordingly. This is one of the ways in which unease about sleeping can become self-reinforcing over time. The mind notices that sleep is hard, and this noticing itself creates tension. The tension sends activating signals through the vagus nerve and the body's other sensory channels to the brain. The brain reads those signals as evidence that arousal is warranted. Arousal increases slightly, sleep becomes harder, and the loop continues. A neuroscientist named Stephen Porges developed a framework for understanding the vagus nerve and the autonomic nervous system that has become enormously influential, not just in neuroscience but in psychology and trauma therapy. He called it polyvagal theory. Porges proposed that the autonomic nervous system does not simply operate in two modes: fight or flight versus rest. Instead, he suggested the system is organized in three levels, reflecting something like the evolutionary history of our nervous system from ancient to more modern circuits. The oldest circuit is what Porges called the dorsal vagal system. When an organism is facing a threat so overwhelming that neither fighting nor fleeing seems possible, this ancient system activates a kind of shutdown response. The heart rate drops dramatically. The body becomes very still. This is the freeze response, sometimes called tonic immobility. It is what happens when a small animal plays dead in the face of a predator that has already caught it. It is extreme conservation. It is, in a sense, the nervous system's last resort. The second circuit is the sympathetic nervous system we have already discussed, the mobilization system, fight or flight, the engine of active response to threat. And the third circuit, which Porges argued is the most recently evolved and the most distinctively mammalian, is what he called the ventral vagal system. This is the part of the parasympathetic system connected to social engagement, to the muscles of the face and voice and ears, to the warmth and openness of genuine connection with others. It is the part of the system that activates when we feel genuinely safe, genuinely seen, genuinely at ease in the presence of other people who mean us no harm. Porges coined the term neuroception to describe the process by which the nervous system continuously scans the environment and other people for cues of safety or danger, largely below the level of conscious awareness. This scanning happens constantly, and it governs which of these three circuits the nervous system is operating in at any given moment. When neuroception reads safety, when the environment is familiar, the people around us are trustworthy, the sounds are gentle and predictable, the body feels held and not threatened, the ventral vagal circuit activates, and with it comes a whole cascade of physiological changes associated with calm, openness, and the willingness to rest. The heart rate variability shifts into a healthier pattern. The facial muscles soften. The voice takes on a warmer quality. And crucially, the higher inhibitory pathways from the prefrontal cortex can now work more effectively, sending those calming signals down to the amygdala that say, "Stand down. Everything is all right." This is the physiological state of feeling safe. And it is, from a neurological perspective, the precondition for genuine, deep, restful sleep. Now let's return to the question of why this state comes so easily to some people and so differently to others. We have already touched on early childhood experiences and the calibration of the stress system. But the story goes even deeper than that, into something that researchers call allostatic load, the cumulative wear and tear on the body and brain from years of chronic stress and sustained activation of the stress response. Think of it this way. The stress response system, the amygdala, the hypothalamic pituitary adrenal axis, the sympathetic nervous system, is designed to operate in bursts. A threat appears, the system activates, the threat passes, the system returns to baseline. That return to baseline is absolutely critical. It is the reset, the restoration, the moment when the body repairs what was used, replaces what was depleted, and readies itself for whatever comes next. But when the threats are chronic, when the environment never truly settles, when tomorrow brings more of the same uncertainty, when the nervous system has learned to treat a low-level hum of danger as the permanent background condition of life, the return to baseline never fully happens. The system stays activated or stays sensitized, and the chemicals of stress become, over time, a kind of new normal. Cortisol levels that were supposed to fall by evening stay slightly elevated. Norepinephrine, the other major stress neurotransmitter, keeps firing, keeping the locus coeruleus, a tiny but powerfully influential structure in the brainstem, at a higher baseline level of arousal. The locus coeruleus, when it fires at high rates, sends norepinephrine broadcasting throughout the brain, amplifying the amygdala's reactivity and making it harder for the prefrontal cortex to exercise its calming influence. This is why people who have been under significant long-term stress often report that they are permanently tired but unable to sleep well. The fatigue is real, the body is exhausted by the sustained cost of stress. But the nervous system is too activated to find genuine rest. It is as if the accelerator and the brakes are both being pressed at once. Research on insomnia has found something quite consistent and rather poignant in this regard. Scientists studying the neurobiology of insomnia have suggested that the vulnerability to develop difficulty sleeping may reside not in the circuits that regulate sleep timing and duration, but specifically in circuits that regulate emotion and arousal, including, most prominently, the sensitivity of the locus coeruleus and its norepinephrine broadcasting system, and the calibration of the amygdala's threat detection threshold. In other words, the people who cannot sleep are not, as a rule, people whose sleep systems are broken. They are people whose arousal systems are too loud. And that loudness almost always has a history. Let's think for a moment about what it means for a nervous system to learn safety. The human brain is a prediction machine. It is constantly building models of the world based on what it has experienced, and using those models to predict what is likely to happen next. This is enormously efficient. It allows us to move through familiar environments quickly, to recognize patterns, to respond appropriately to the usual run of events without expending enormous mental energy on each individual moment. But this predictive capacity also means that the brain is not reacting to what is actually happening right now so much as to what it expects to happen, based on what has happened before. Your brain in the present moment is partly a conversation between right now and the recorded history of your experience. This is why walking into a room that is associated with something difficult in your past can make your body tense before you have consciously identified what is bothering you. The amygdala has the memory, often an implicit memory, a body memory, a felt sense rather than a clear recollection, and it fires before the cortex has had time to evaluate. And it is also why the experience of safety, genuine and repeated safety, can slowly change things. Because the brain's predictions are not fixed. They are continuously updated by new experience. This is the essence of neuroplasticity, the brain's remarkable capacity to reorganize itself, to strengthen connections that are used and let others fade, to write new predictions based on new evidence. When a person who has learned to be vigilant begins to have repeated experiences of genuine safety, when they rest in a familiar place and nothing bad happens, when they let their guard down slightly and the world does not punish them for it, when they receive consistent evidence over time that this particular environment, this particular time of day, this particular set of conditions is actually safe, the amygdala begins slowly but genuinely to recalibrate. The prefrontal cortex, if given consistent, calm, positive experience to work with, can build and strengthen its inhibitory pathways. The override switch, the one that says to the amygdala, you don't need to stay on alert right now, can become more practiced, more efficient. The ventral vagal system can become more easily accessible, more responsive to the cues of safety that are actually present in the environment. This is not magic. It is neurobiology. And it takes time, and it often takes more than good intentions. It takes conditions that genuinely support the nervous system in having these new experiences. But it is real. The nervous system can learn safety. It learned to be vigilant from experience, and it can learn to rest from experience too. There is something else happening in the brain while we sleep that is directly relevant to all of this, and it is one of the more beautiful discoveries in recent sleep science. While you sleep, your brain is not simply resting. It is actively working on your emotional landscape. During REM sleep, the stage of sleep characterized by vivid dreaming and rapid eye movements, which typically first appears about 90 minutes after you fall asleep and then recurs in longer and longer periods throughout the rest of the night. The brain engages in a process that researchers have described as emotional memory reprocessing. The memories of emotionally significant experiences from the day are replayed and re-encoded, but this time in a neurochemical environment that is notably different from waking. During REM sleep, levels of norepinephrine, that arousing, alarm-related neurotransmitter we discussed earlier, fall to their lowest point of the entire 24-hour cycle. This is unique. Norepinephrine is present throughout the brain during wakefulness and even during non-REM sleep. But during REM sleep, the locus coeruleus essentially goes quiet. The brain is replaying emotional content, but doing so in the absence of the neurochemical that normally accompanies fear and stress. Scientists, including the neuroscientist Matthew Walker, have described this as the brain's built-in overnight therapy. The emotional sting of difficult memories is processed and integrated during REM sleep, and when you wake, the memory remains. But the acute emotional charge associated with it may be somewhat reduced. The experience has been metabolized, at least partially, into something more tolerable. This is also why sleep is so critical for distinguishing between genuine threats and non-threats. Research has shown that with good sleep, the brain becomes better at a kind of emotional calibration, more able to identify what actually deserves a fear response and what does not, more able to maintain the nuanced spectrum between danger and safety rather than collapsing everything into alarm. And conversely, research has shown that sleep deprivation dramatically degrades this calibration. After a poor night of sleep, the amygdala becomes more reactive, more likely to fire in response to stimuli that would not normally trigger it, more likely to treat ambiguous information as threatening, less able to distinguish a worried face from an angry one. The prefrontal cortex's ability to send calming, contextual signals to the amygdala is also reduced when sleep is poor. The connection weakens. The override switch becomes less reliable. This creates a potentially difficult loop. Fear and hypervigilance make sleep harder to achieve, and poor sleep makes fear and hypervigilance worse. The systems reinforce each other in both directions. But understanding this loop is the first step toward interrupting it. Let's think about the hippocampus now, because it plays a fascinating and often underappreciated role in the story of sleep and safety. The hippocampus is a curved, seahorse-shaped structure buried deep in the temporal lobe of the brain, one on each side. It is the part of the brain most associated with memory formation, particularly the kind of memory that involves context, where things happened when they happened, what the surrounding circumstances were. The hippocampus, in the context of safety and threat, plays a particularly important role in what researchers call contextual fear, the understanding that a thing that was once dangerous in one context might not be dangerous in another context. This context-dependent learning is critical for adaptive behavior. A loud sound in a forest at night is genuinely alarming. The same loud sound in a sports stadium full of cheering people is completely benign. The hippocampus holds the contextual information that allows the brain to make that distinction. And during sleep, particularly during slow-wave sleep, the deep, restorative phases of non-REM sleep, the hippocampus consolidates the memories of the day, transferring important information from its temporary storage to longer-term networks in the neocortex. This consolidation process, this nighttime replaying and filing of experience, is one of the most important things sleep does. Without it, we cannot learn effectively, cannot form reliable memories, cannot update our predictions about the world. Research has also found that during sleep, the hippocampus and the prefrontal cortex work together in a kind of coordinated dialogue. The hippocampus replays recent experiences, and the prefrontal cortex helps to integrate those experiences into the larger architecture of existing knowledge and belief. This is partly how we come to understand, over time, that a place that was once associated with danger can become genuinely safe. The contextual memory of accumulated safe experience in that place, consolidated during sleep night after night, eventually updates the prediction. This is one of the reasons why sleeping in a new place can be difficult even for people who generally sleep well. The brain has not yet built a consolidated library of safe experience in that context. There is no accumulated overnight evidence that this room, these sounds, this darkness is trustworthy. The hippocampus is still gathering data. And the amygdala, working from an incomplete record, stays a little more alert. For people who have a history of feeling unsafe in sleep environments, this contextual updating can take much longer to build. But it does happen. Night after night of waking up unharmed, night after night of the world being as quiet in the morning as it was when they lay down, this evidence accumulates. The prediction slowly, gradually shifts. By this point, you may be feeling something interesting, a kind of soft, steady curiosity, a sense of ideas moving through you gently, not agitating but illuminating. And perhaps, if you are one of the people who find sleep difficult, you are feeling something else too. A kind of recognition, a quiet ache of acknowledgement that some of what I have been describing sounds familiar. That the vigilance I am talking about, the nervous system that cannot quite release, is something you know from the inside. If so, I want to sit with that for a moment. Not to fix it, not to offer a prescription, but just to acknowledge it. Because one of the most important things that sleep science has consistently found is this: the experience of hypervigilance, of being unable to relax, of lying awake in the dark feeling watched by some interior alertness that you didn't ask for and can't seem to turn off. This is not weakness. It is not a failure of character or will or intelligence. It is the nervous system doing exactly what it learned to do, in the conditions where it had to do it, with the information it had at the time. It is a system trying, as it always is, to protect you. Sometimes that protection becomes outdated. Sometimes the system that kept you safe in one context follows you into contexts where it is no longer needed. And the system, being a system without language or self-awareness, cannot simply be told that the danger has passed. But it can learn. Gradually, patiently, with the right kind of evidence and care and time. Let's talk now about the body's own chemistry of calm, the natural biological signals that tell the brain it is time to ease into sleep. Melatonin is perhaps the most well-known of these signals. Produced by the pineal gland, a tiny pinecone-shaped structure deep in the brain, melatonin is released in response to darkness. As light levels fall in the evening, a region of the hypothalamus called the suprachiasmatic nucleus, the brain's master biological clock, made up of roughly 50,000 neurons that receive light information directly from the retina, begins to signal the pineal gland to start its melatonin production. Melatonin does not knock you out the way a sedative would. It does not force sleep. What it does is more subtle and more important. It tells the brain what time it is. It synchronizes your internal biological clock with the natural rhythm of night. It says chemically to every system in the body, the day is done, the darkness is here, and it is now appropriate to begin the transition toward rest. And melatonin works in close coordination with cortisol. They move in opposite rhythms throughout the day. As cortisol rises in the morning, melatonin falls. As melatonin rises in the evening, cortisol should fall. This reciprocal dance is one of the most elegant examples of biological regulation in the human body. When the dance works correctly, you feel energized in the morning, increasingly calm through the evening, and genuinely sleepy by bedtime. But when the stress system is running high, when the amygdala is keeping the cortisol elevated past its natural evening decline, the cortisol-melatonin balance tips. Melatonin cannot fully exert its quiet authority. The brain remains more alert than it should be at the biological time for sleep. And the body pays a price for this disruption that extends far beyond a single bad night. Chronic disruption of this cortisol-melatonin rhythm, which is often what sustained stress or anxiety does, has been associated with a wide range of health consequences, not just poor sleep, but effects on metabolism, immune function, cardiovascular health, and the long-term health of the brain itself. The brain is trying, with melatonin, with the gradual decline of cortisol, with the slow cooling of body temperature in the evening, another circadian signal for sleep onset, with the accumulation of adenosine, the sleepiness chemical that builds in the brain with each waking hour, to create the right conditions for you to let go. It is preparing the way. And sometimes, when the nervous system's arousal signal is too strong, all of those preparations simply cannot overcome it. There is a structure I have not yet mentioned, but which deserves a moment of quiet attention. It is called the ventrolateral preoptic nucleus, and it sits in the hypothalamus, and it has one very specific job. It promotes sleep by inhibiting the brain's arousal centers. When the ventrolateral preoptic nucleus becomes sufficiently active, when the brain's various signals for sleepiness have reached a certain threshold, when the circadian clock says it is time, when the parasympathetic system is dominant, when melatonin is flowing and cortisol is low, this structure begins to suppress the wakefulness-promoting regions of the brain. The locus coeruleus, with its norepinephrine, the tuberomammillary nucleus, with its histamine, the dorsal raphe nucleus, with its serotonin in its wake-promoting form. All of these regions, which collectively maintain the alert, engaged state of wakefulness, begin to be quieted by this small but decisive group of neurons. Sleep researchers sometimes describe this as a kind of flip-flop switch, a system that moves quickly between the two states of sleep and wakefulness, rather than fading gradually. The transitions can be nearly instantaneous on the timescale of neural events, even when they seem gradual from the outside. You are awake and then you are asleep. The switch flips. But for the switch to flip toward sleep, the conditions must be right. And the most important condition of all is that the arousal systems must be willing to be quieted. If the locus coeruleus is still firing at a high rate, if norepinephrine is still broadcasting its waking, alerting message throughout the brain, the ventrolateral preoptic nucleus cannot overcome it. The switch stays in the wake position. The person lies there, tired, wanting sleep, physiologically unable to find it. This is not just frustrating. This is genuinely uncomfortable. The body is holding two incompatible states simultaneously. The fatigue that comes from hours of wakefulness, and the arousal that prevents rest. And the mind, caught between them, often reaches for the only tool it knows: thought. Rumination, going over the events of the day, planning for tomorrow, replaying things that were said and unsaid, worrying about things that may or may not come to pass. This rumination is not a cause of sleeplessness so much as a symptom of it. The busy mind is what an aroused brain does when the body it inhabits is lying still in the dark and there is nothing externally to engage with. The solution is not to stop thinking. That is like telling a startled cat to be still, but to give the arousal system a reason to settle. To provide the brain with genuine evidence of safety. To find a way, however gradually, to help the nervous system shift modes. So how does this shift happen? How does a nervous system that has learned vigilance begin to learn or relearn what safety feels like? The answer is beautifully consistent across many different lines of research, and it comes down to something very simple: repetition. The slow, patient accumulation of evidence. Recall what we said about the brain as a prediction machine. It builds its predictions from experience, and it updates those predictions when new experience consistently contradicts the old ones. The nervous system that expects danger can, over time, begin to expect something different if it is given enough experiences that gently, reliably tell a different story. This is what makes consistent bedtime routines so neurologically significant. Not because they are relaxing in some abstract sense, but because they give the brain specific, repeated, contextual cues, the same sounds, the same light level, the same temperature, the same sequence of events, that over time become associated with the transition to sleep. The hippocampus logs this context. The predictive brain begins to expect that when these cues are present, what follows is rest. And the amygdala, receiving this prediction from the hippocampus and the prefrontal cortex, begins to ease its vigilance a little earlier, a little more reliably. This is also why social safety, the felt sense of being with other people or in a place associated with people who are genuinely trustworthy, is one of the most powerful triggers for the ventral vagal state we discussed. The human nervous system, unlike that of many other animals, appears to have evolved to use social connection as one of its primary cues of safety. We are social animals, and historically, being alone at night while others slept meant exposure to cold, to predators, to the 100 dangers of the ancient world. Being embedded in a group, hearing the quiet breathing of others, smelling the familiar scent of people who meant no harm. These things were survival itself. This is partly why so many people sleep better with a partner or with a pet or even with the sound of a television in the background. Not because the noise helps, but because the sonic presence of other beings, even simulated ones, provides the neuroceptive cue: I am not alone. There is social presence here. The ventral vagal system reads this as safety, and the arousal system's ease. There is one more thing I want to say about this because it seems important, and because it is something that science keeps returning to with considerable consistency. The body has its own wisdom about safety, and much of that wisdom is held not in the conscious mind but in the body's sensations, in the quality of the breath, the softness of the belly, the heaviness of the limbs, the slowness of the heartbeat. When people are in a state of hypervigilance, they often experience a kind of disconnection from these bodily cues. The mind races. The attention is directed outward, scanning the environment, or inward in a very cognitive way, thinking, planning, worrying, rather than resting in direct awareness of the body's present moment experience. This outward and cognitive form of attention actually tends to maintain the arousal state because it keeps the predictive, anticipatory machinery of the brain running. Practices that redirect attention toward direct, non-evaluative awareness of bodily sensation, what clinicians often call somatic awareness or interoception, have been shown in research to have measurable effects on autonomic nervous system regulation. They strengthen the connection between the higher cortical regions and the body monitoring pathways of the vagus nerve and the insular cortex. They help the brain receive the body's own calming signals more clearly. They, in effect, help the nervous system learn to read its own evidence of safety. Slow, deliberate breathing is perhaps the simplest and most well-documented of these practices. A long, slow exhale, longer than the inhale, directly activates the vagal brake, the parasympathetic override on the heart rate. The heart slows measurably. The body sends a signal upward. I am settling. The brain receives it. Progressive relaxation of muscle groups, starting at the feet and moving slowly upward, simply noticing and releasing tension, engages body awareness in a way that gives the nervous system physical evidence of the body's willingness to let go. Muscle relaxation sends its own parasympathetic signal up through the body's monitoring systems. The brain registers the softening. These are not tricks. They are not performance. They are the body teaching the brain, through its own language, that it is safe to rest. And over time, with repetition, the brain begins to believe what the body is consistently telling it. The pathways strengthen. The amygdala learns to receive the quieting signals more readily. The ventral vagal state becomes a little more accessible than it was before. I want to return, before we begin to draw this night gently to a close, to the person on the airplane. The one who fell asleep within minutes in what seemed like impossible conditions. I think, having traveled through all of the science together, we can understand them a little differently now. Not as someone lucky or gifted or fundamentally different in some enviable way, but as someone whose nervous system, perhaps through the good fortune of early experience, perhaps through deliberate practice, perhaps through some combination of temperament and environment and time, had learned a very simple thing. It had learned that it was generally all right to let go. Not that the world was without danger, no nervous system could or should believe that. Not that vigilance is never warranted, sometimes it genuinely is. But that, in the absence of clear and present evidence of threat, the default state could be rest, could be softness, could be the quiet confidence that the world would still be there, that the body would still be intact, that waking could be trusted to take care of itself when it came. This is not certainty. This is a calibration. A learned relationship between the brain's prediction system and the reality of a world that is, for most of us, most of the time, genuinely not dangerous in our beds at night. And if your nervous system has not learned this calibration yet, if you are someone who carries your vigilance into the dark with you, who finds the act of letting go genuinely difficult, who lies awake listening to the house's quiet sounds and translating them into questions, please hear this with every bit of warmth I can put into it. Your nervous system is not broken. It is not wrong. It is doing exactly what it was shaped to do. And it has the capacity to learn something new. Learning takes time. The nervous system is not recalibrated in a night, but it can be moved, can be gently, patiently redirected. Every night that passes in safety is, in some small way, new data for the predictive brain. Every slow exhale in the dark is a vote cast for rest. Every morning that arrives without catastrophe is quiet evidence that the world, here, now, is safe enough. The hippocampus is filing all of it. The prefrontal cortex is slowly, incrementally strengthening its calming pathways. The amygdala is, night by night, receiving a slightly different set of signals to compare its calculations against. It is slow work, and it is honest work. There are no shortcuts through the neurobiology of trust. But there is also no ceiling on what the nervous system can learn. The brain that learned vigilance learned it because it was capable of learning. And that same capable, plastic, endlessly adaptive brain can learn something else. So here you are, in your bed, in the dark, at the end of this long and gentle journey through the science of feeling safe. Your brain is somewhere above you, behind your eyes, inside the quiet dark of your skull, doing all the things we have talked about. The amygdala is there. It's scanning, slowing as the familiar sounds of this place accumulate around it without incident. The prefrontal cortex is there, sending its measured, calming signals downward. The vagus nerve is running its long, branching path through your chest and belly, monitoring and feeding back and adjusting. The ventrolateral preoptic nucleus is building toward the moment when it will begin to quiet the last of the wakefulness systems. Melatonin is already moving through your bloodstream. Cortisol is at its low. The night is doing its work, and your body is doing its work too. With every slow breath, with every exhalation that is slightly longer than the breath before it, with every small release of tension in your shoulders, your jaw, your hands, your body is broadcasting upward through all of the ancient and intricate channels of the nervous system, a message that has been meaningful for as long as nervous systems have existed. It is safe here. You can let go now. Take a breath. Just a breath, and feel the weight of your body against the surface beneath you, not heavy in a bad way, just present, grounded. Here, your legs are resting. They carried you through today and now they are resting. Your arms are resting. They held and reached and typed and cooked and now they are resting. Your chest is rising and falling with a steady, unhurried rhythm. Your heart is beating at whatever rate it has settled into in this quiet. You don't need to change any of it. You don't need to regulate or control. You only need to notice softly, the way a scientist notices something, with calm curiosity, without urgency. Your brain is still there, still active in its quiet way. But listen to how the thoughts are beginning to thin out. They come and they drift, they come and they drift. You are not your thoughts right now. You are the space they are moving through. The amygdala is settling. Not because there is no alarm in it, but because the evidence is accumulating quietly and persistently that there is nothing here that requires its full attention tonight. The world outside this room is going about its own affairs. The night is soft. The room is still. You are here. There is a concept in neuroscience called extinction, and despite the slightly ominous sound of the word, what it refers to is actually one of the most hopeful processes in the whole of brain science. Extinction is what happens when a learned fear response begins to fade because the feared thing consistently fails to occur. The brain had learned, through experience, to expect something. It kept that expectation coded in its circuits because that was the adaptive thing to do. But when the expected thing stops happening, when the cue appears and the threat does not follow again and again and again, the brain gradually rewrites the prediction. The old fear association does not disappear exactly, but a new layer is written on top of it. A new learning, a new expectation. This new learning is fragile at first. It needs reinforcement. It needs time and repetition to become as strong as the original fear learning. But it is real. It is measurable. Scientists can see it in changes in amygdala activity, in changes in prefrontal connectivity, in changes in the kinds of neural oscillations the brain produces in response to formerly feared stimuli. And sleep, the research is very clear on this, is one of the most important periods for consolidating this new learning. The memories of safe experience are replayed during slow-wave sleep. The emotional recalibration happens during REM sleep. The new prediction, the one that says this is safe, this is fine, you can rest here, is strengthened during the hours of the night while you lie still and the brain does its quiet work. Every safe night helps build the case. Every morning without catastrophe is another gentle reinforcement of the new story. The nervous system, learning to believe in safety, consolidates that learning while you sleep. And the deeper and more restful the sleep, the more effectively that consolidation occurs. This is one of those beautiful loops where the cure and the condition improve together. Better sleep builds safer nervous systems, and safer nervous systems sleep better. The work of each night underpins the work of the next. You are very close to sleep now. I can feel it in the pacing of these words, the way the sentences have been stretching and slowing, the way the ideas have been arriving more gently, with longer pauses between them. There is nothing more you need to understand tonight. Everything that needed to be explained has been explained. Your brain has received it all, absorbed it quietly, filed some of it away for later, let some of it wash through without catching, and perhaps found in the listening itself something that settled the nervous system in a way that is hard to put into words but easy to feel. That is the other thing about spoken language, about the right voice, the right rhythm, the right register. Language itself can be a safety cue. The predictable cadence of a calm voice, the warmth and unhurriedness of a tone that is not demanding anything, not alarming about anything. This registers in the nervous system as social safety signal. The ventral vagal system, remember, is connected to the muscles that read voices and faces. It is tuned exquisitely to the sound of a person who is not afraid. And a person who is not afraid, speaking quietly in the dark, is one of the oldest and most reliable cues of safety the nervous system knows. So I will stay here with you for just a little longer as you drift. The science of sleep is still young in the larger scheme of things. Humans have been sleeping since long before any of us could articulate what sleep was for, and we are still, in many ways, just beginning to understand the full depth and complexity of what happens in those dark hours. New discoveries arrive regularly about the glymphatic system, the brain's overnight waste clearance mechanism that washes cerebrospinal fluid through the spaces between neurons while you sleep, sweeping away the metabolic byproducts of a day's worth of thinking. About the way REM sleep appears to selectively process and integrate emotional experience. About the precise molecular mechanisms by which sleep strengthens some synaptic connections while allowing others to quiet. There is so much we do not yet know. But one thing the science keeps returning to from every angle with every methodology in every population studied is this: Sleep is not passive. It is not the absence of something. It is a profoundly active, profoundly important state. Perhaps the most important state the brain enters in its entire daily cycle. And the foundation of that state, the thing that allows the brain to enter it and stay in it and do all of the extraordinary things it does there, is safety. The felt, embodied, neurologically grounded sense that here, now, in this place and this moment, it is okay to let go. Your body is heavier now, or it feels that way. The boundary between where you end and where the mattress begins has grown soft and indistinct. Your breathing is slower. It moves through you without effort now, without any particular direction from you. The body knows how to breathe. It has been doing it since long before you were conscious of it, and it will go on doing it without you having to think about it at all. Somewhere in your prefrontal cortex, the last few attentive thoughts are beginning to loosen their grip. The train of ideas is slowing, the cars drifting apart, the connections between them growing tenuous and soft. The amygdala has, for now, accepted the evidence. The scanning has quieted. The alarm is on a very low setting. Not off, the brain is never entirely off, but low enough that it will only stir if something genuinely warrants it. And nothing here warrants it. Nothing here is asking anything of you. Your hippocampus is already beginning its nightly work, quietly cataloging the threads of the day, preparing to file them away in the larger structure of your life's knowledge during the long, slow waves of deep sleep that are coming. Your body temperature has dropped slightly, as it always does in the hours before and during sleep, a beautiful automatic feature of circadian biology, the body's own way of creating the cool conditions that deepen sleep. And melatonin, that quiet, dark hormone, the body's own night signal, is flowing through you, finding its receptors in the suprachiasmatic nucleus and beyond, anchoring you gently to the rhythm of the night. All of this is happening, all of it right now without any effort from you. The body knows the way. It always has. Let me leave you with this. Wherever your nervous system is right now, whether it is easy and quiet and nearly gone, or whether it is still holding a small flame of alertness, still listening, still waiting, it is doing its best for you. It has always been doing its best for you. Everything it learned because at some point that learning seemed necessary. Everything it holds on to because somewhere in its deep library of experience, that holding on was connected to something important. And it can learn new things. It is learning new things right now, this very moment, in the quiet and the dark. Every breath you take in safety is new experience. Every moment you rest without harm is data for the predictive brain. The amygdala is listening to all of it, and the hippocampus is filing it, and somewhere in the slow work of the coming night, while you are gone to sleep, all of that new data is being woven into the fabric of the brain's expectations. Tomorrow's nervous system will be, in small but real ways, different from today's. More practiced at this. More familiar with what tonight felt like. More likely to expect it again. That is neuroplasticity. That is the extraordinary quiet power of a brain that never stops learning. That never stops being capable of something new. You are that brain. You are that nervous system. And you are, right now, exactly where you are supposed to be. Sleep well. Let the sounds of the room settle around you like something familiar and kind. Let the darkness be not empty but full of quiet, full of the hum of a world going gently about its own affairs, not requiring anything of you. Let your body be heavy and warm and held by the surface beneath you. Let your thoughts come and go like weather. Let the breath move through you of its own accord. And know, somewhere in the part of you that is still softly listening, that you are safe here. That this is a safe place, a safe time, a safe body to rest in tonight. The science says so. The biology says so. The long, slow accumulation of this night's evidence says so. You are safe. You can sleep now. If tonight's story brought you something, a little more softness, a little more understanding of your own biology, a little more peace in the dark, please consider sharing Deep Science Sleep with someone else who might need it. And if you haven't already, subscribing to the channel means you'll never miss a night of science told gently, the way we like to tell it here. Sleep well, and we'll see you in the next one. End of script. Approximately 19,200 words asterisk. There is something happening right now, even as we speak, that I have been saving for this point in the night. A piece of biology so elegant, so quietly extraordinary, that I think it deserves its own space, its own unhurried telling. While you are awake, your brain is working. Every thought, every perception, every memory retrieved, every emotion processed, all of it costs something. The neurons doing that work consume oxygen and glucose, and as they do, they produce metabolic byproducts. The chemical residue of a day's worth of thinking. And unlike the rest of your body, which has a network of lymphatic vessels to carry away cellular waste, the brain exists inside a closed skull with no conventional lymphatic drainage. For a long time, this was a genuine puzzle for neuroscientists. How does the most metabolically active organ in the body, the brain, uses roughly 20% of the body's entire energy supply despite being only about 2% of its weight? How does it clear its own waste? The answer was discovered only in 2012 by neuroscientist Maiken Nedergaard and her team at the University of Rochester. And it is one of the most remarkable revelations in recent brain science. The brain has its own dedicated waste clearance system. It is called the glymphatic system, a name that combines glial, referring to the brain's supporting cells, and lymphatic, after the function it mirrors. Here is how it works. Cerebrospinal fluid, the clear, protective liquid that surrounds and cushions your brain and spinal cord, does not merely sit still. During sleep, it flows through a network of channels that run alongside the brain's blood vessels. Tiny spaces wrapped in the end feet of cells called astrocytes, which are a type of glial cell. These astrocytes are equipped with water channels called aquaporin, 4, which open up during sleep to allow the cerebrospinal fluid to flow through at a dramatically faster rate than during waking hours. This flowing fluid does something profound. It moves through the brain's tissue, mixing with the fluid between neurons and their supporting cells, the interstitial fluid, and as it does, it acts like a slow, thorough rinsing. It sweeps up metabolic waste products, proteins that accumulated during the day's neural activity, and carries them out of the brain to be cleared away by the body's lymphatic system in the neck. Nedergaard's team found, in their original experiments in mice, that this cerebrospinal fluid flow increased by an extraordinary factor during sleep. The fluid movement was roughly 10 times more vigorous during sleep than during wakefulness. 10 times. The interstitial space between cells appeared to actually expand during sleep, widening by around 60%, allowing much greater fluid movement. And subsequent research has extended these findings to the human brain. Scientists using magnetic resonance imaging have observed the rhythmic pulsing of cerebrospinal fluid in sleeping humans, flowing in waves that are coupled to the brain's own slow electrical oscillations and to the steady rhythm of the heartbeat. The brain, during sleep, is not simply quiet. It is being washed. Among the waste products most efficiently cleared by this nightly rinse is amyloid beta, a protein that, when it accumulates over years, forms the characteristic plaques associated with Alzheimer's disease. The connection between poor sleep and elevated amyloid beta accumulation in humans has now been documented in multiple studies. A single night of poor sleep is enough to produce a measurable increase in amyloid beta concentration in the brain's interstitial fluid. Years of disrupted sleep, researchers believe, may contribute meaningfully to the long-term risk of neurodegenerative disease. This is one of the more sobering discoveries in recent neuroscience. Sleep is not merely a passive rest. It is an active nightly maintenance program, a biological cleaning service that the brain has apparently evolved specifically to require the offline state of sleep in order to operate. And here is something particularly beautiful about how this system works in relation to everything we have been discussing tonight. The glymphatic system operates most powerfully during slow-wave sleep, the deep, restorative stage of non-REM sleep that produces the large, rolling electrical waves visible on an EEG as the brain slips into its most profound rest. And the activation of the glymphatic system is directly connected to a reduction in norepinephrine. The same norepinephrine that we discussed earlier, the neurotransmitter of the locus coeruleus, the arousal center, the nervous system's alerting signal. When norepinephrine falls, as it does during deep sleep when the locus coeruleus quiets, the astrocytes' water channels open more fully, the interstitial space expands, and the cerebrospinal fluid flows in to do its work. In other words, the very same neurochemical state that allows you to feel genuinely safe and to sleep deeply is the state that triggers the brain's own purification system. The nervous system that can relax, that can let norepinephrine fall, that can let the locus coeruleus quiet, does not just sleep better. It cleans its own house more completely. It maintains itself more thoroughly. It replenishes itself at a cellular level in ways that the vigilant, over-aroused nervous system simply cannot access. Feeling safe enough to sleep deeply is, quite literally, one of the most nourishing things you can do for your brain across the long arc of a lifetime. And while all of that extraordinary cleaning is happening, while the cerebrospinal fluid is sweeping through the spaces between your neurons like a slow, gentle tide, something else is unfolding in the brain that is equally beautiful, and that connects directly to the story of how the nervous system learns to feel safe over time. During the deep stages of non-REM sleep, the brain generates a particular kind of electrical activity that researchers have studied with great care. It consists of large, slow waves, the brain's electrical equivalent of a long, deep exhale. These waves arise in the cortex and sweep from front to back, and as they travel, they produce a rhythmic alternation between activity and silence. A brief moment of neural firing, called the up state, followed by a period of profound quiet, called the down state, in which cortical neurons fall nearly silent for a fraction of a second before rising again. This alternating rhythm up, down, repeating slowly through the deep hours of the night, is believed to serve a function that is as elegant as it is important. Neuroscientists Giulio Tononi and Chiara Sorelli have called it the synaptic homeostasis hypothesis, and here is what it proposes. During the hours of wakefulness, as you learn things and experience things and encounter the world, the connections between your neurons, the synapses, are being constantly strengthened. Every new fact, every new experience, every association made and emotion felt strengthens certain neural pathways. This is neuroplasticity in action, the brain physically changing in response to experience. But this strengthening cannot go on indefinitely. Synapses have a physical and energetic cost. As more and more of them become stronger throughout the day, the brain's overall metabolic load increases. The signal-to-noise ratio across the neural landscape begins to degrade. There is more and more background activity, more random firing, less clarity about which signals are truly important and which are just noise. The slow waves of deep sleep, Tononi and Sorelli propose, solve this problem. As the slow waves sweep through the cortex, they produce a global, gentle downscaling of synaptic strength. The weaker connections, the ones that were strengthened only a little during the day, the ones corresponding to passing experiences and incidental details, are allowed to fade back toward their baseline. The stronger connections, the ones representing the most important learning of the day, are preserved. What happens over a night of good, deep sleep is a kind of neural editing. Not erasure, but refinement. The brain, during its down states, is sorting through the day's accumulation of experience and gently adjusting the signal levels, turning down the noise, preserving the essential, restoring the clarity that will allow tomorrow's learning to happen against a clean background. When you wake from a night of truly deep sleep, there is often a quality of mental clarity that is hard to describe from the inside. A sense that things are somehow more in focus, that thoughts come more cleanly, that the world has a crispness it lacked when you went to bed exhausted. That quality is partly this. The synaptic landscape of your cortex has been gently restored to its productive baseline. The slate has been not wiped but carefully prepared for what comes next. And this process, like the glymphatic cleaning, depends on the nervous system being able to reach that deep, slow-wave sleep. It depends on the body being able to let the arousal systems go quiet enough, for long enough, that the slow oscillations can establish themselves and do their work. This is another way in which the quality of felt safety has long-reaching consequences. Not just for tonight's rest, but for the clarity and efficiency of tomorrow's mind. Now let's spend a little time with adenosine, because adenosine is one of the most important and least talked about molecules in the entire story of sleep, and it is doing something quite significant in your body right now. Adenosine is a natural byproduct of cellular activity, of neurons firing, of ATP, the basic energy currency of cells, being broken down and used. As you go about your day, as your neurons work, adenosine accumulates in the brain's extracellular space. It builds up gradually, hour by hour, as a kind of chemical record of how long you have been awake. And adenosine, as it accumulates, binds to receptors on neurons throughout the brain and produces a very specific effect. It quiets the activity of the brain's arousal systems. It inhibits the very neurons that keep you awake. It begins to suppress the locus coeruleus, the histamine-producing tuberomammillary nucleus, the orexin-producing neurons of the lateral hypothalamus, all the structures that maintain the alert, engaged state of wakefulness. The more adenosine has accumulated, the more strongly these systems are being dampened, and the more powerfully you feel the pull of sleep. This is sleep pressure. This is the homeostatic drive for sleep that builds across every waking hour, regardless of whether the clock has moved from morning to night. The adenosine builds, the arousal systems are increasingly suppressed, and the ventrolateral preoptic nucleus, the sleep-promoting region we discussed earlier, finds it easier and easier to tip the balance toward rest. Incidentally, this is exactly how caffeine works. Caffeine does not give you energy in any direct sense. It does not produce arousal on its own. What it does is block adenosine receptors. It slips into those receptors before adenosine can, like a key that fits the lock but does not open the door. With adenosine blocked from its receptors, the suppression of the arousal systems is relieved, and wakefulness is maintained. But crucially, the adenosine is still there, still accumulating. When the caffeine wears off, when the adenosine finds its receptors again, all that built-up sleepiness comes flooding in at once, the familiar crash that follows a long caffeine-sustained day. But in the absence of caffeine, adenosine is doing exactly what it is supposed to do tonight. It is accumulating in your brain right now as we speak, as the hours of your waking day have passed, and it is working alongside melatonin and the falling cortisol and the cooling body temperature to create the chemical conditions under which the ventrolateral preoptic nucleus can finally tip its switch, under which the slow waves can begin, under which the glymphatic system can open its channels, under which you can rest. Adenosine is your body's own patient, biological argument for sleep. It has been building its case all day, and now, in the quiet of this room, in the dark of this night, with the day's obligations behind you, it is at its most persuasive. Let's return one more time to something we touched on earlier, the remarkable molecule called oxytocin. Because oxytocin plays a role in the biology of feeling safe that deserves more than a passing mention. Oxytocin is produced in the hypothalamus, specifically in a region called the paraventricular nucleus, and it is released into the brain and the bloodstream by the pituitary gland. You may have heard oxytocin described as the love hormone or the bonding hormone, and those names are not inaccurate, though they underrepresent the full scope of what this molecule does. Oxytocin is released in a wide variety of social contexts. During physical touch, during eye contact with someone trusted, during the warmth of a genuine conversation, during the feeling of being understood by another person, during the closeness of sleeping beside a partner or a child or even a beloved animal. Its release is also stimulated by warmth against the skin, which may partly explain why a warm bath before bed has such a reliable calming effect. When oxytocin enters the brain, it acts on receptors in the amygdala and produces something quite specific. It reduces the amygdala's fear response. Research has consistently shown that oxytocin binds to receptors in the amygdala's threat detection circuits and quiets them. The alarm system in the presence of oxytocin becomes less reactive. The threshold for firing rises. Stimuli that would normally trigger a fear response are processed as less threatening. At the same time, oxytocin shifts the balance of the autonomic nervous system toward parasympathetic dominance. The rest and digest branch, the branch that allows the heart to slow, the breath to deepen, the muscles to release. And oxytocin suppresses cortisol, the stress hormone that competes with melatonin, quieting the HPA axis and allowing the body's evening chemistry of calm to proceed unimpeded. In the language of polyvagal theory, oxytocin is one of the primary activators of the ventral vagal state, that most distinctively mammalian mode of safety and social connection that Stephen Porges identified. The feeling of being safe with others, the sense of belonging and trust, the ease and openness of genuine connection. All of this is partly mediated by oxytocin acting on the nervous system. This is part of why the presence of another trusted person is one of the most powerful sleep aids that biology has ever devised. Not simply because another person provides companionship or distraction, but because the nervous system of a mammal is exquisitely calibrated to read the physiological signals of another mammal's calm. Their breathing rate, their warmth, the subtle social cues of relaxed muscles and soft voice, and to interpret all of it as evidence of safety. In the presence of those signals, oxytocin rises, the amygdala quiets, the parasympathetic system deepens its hold. Sleep becomes more accessible. Even the memory of a trusted person, research has found, can produce some of this effect. Researchers studying what they call secure attachment priming have shown that briefly thinking of someone with whom you feel deeply safe, really calling up the felt sense of their presence, the warmth of being with them, can measurably reduce amygdala reactivity to stress. The oxytocin system can be engaged not just by physical presence, but by something like the embodied memory of safety. The brain, finding the right association, releases the molecule that quiets its own alarm. And this means that the memories of genuine safety and genuine connection that you carry, whoever gave them to you, a person or a place or a pet or a moment in time, those memories are not just pleasant reminiscences. They are neurobiological resources. They are, quite literally, available to the nervous system as medicine. You do not need to manufacture a feeling tonight. You do not need to convince yourself of anything you do not genuinely feel. But if there is a memory of warmth and safety that comes naturally, a person, a place, a moment when the world felt exactly right, let it rest in your awareness. Gently, without effort, simply notice what happens to your breathing. There is one more dimension of this story that I want to share with you before we draw the night gently to its close. And it is perhaps the most ancient dimension of all. Consider for a moment what sleep must have been like for our earliest ancestors. Not in a house, not in a bed, not in a room with a door that locks. In a forest or a savanna or the entrance to a cave. In the dark, in the open, in a world that genuinely did contain dangers that could arrive in the night. How did they sleep at all? The answer, many anthropologists and evolutionary biologists believe, is that they slept together. Human sleep, the particular architecture of our sleep cycles, the timing of our circadian rhythms, the way our sleep is structured to include periods of lighter sleep at regular intervals throughout the night, may in part reflect an evolutionary history of sleeping in social groups, where the vigilance of the group as a whole allowed individual members to cycle through deeper sleep at different times, creating a kind of distributed awareness that no individual could maintain alone. There is fascinating research on hunter-gatherer communities today that suggests this may still operate in traditional contexts. Studies of the Hadza people of Tanzania, for example, have found that across the community's sleep patterns, there are very few moments of the night when everyone is simultaneously in the deepest stages of sleep. Individual sleep stages cycle in and out of synchrony, creating what the researchers described as watch periods. Times when at least some members of the group are in lighter sleep, more responsive to the environment, while others are in deeper rest. The group in this model is itself a sleep infrastructure. The social body becomes the safety net that allows individual biological vulnerability. This deep evolutionary context helps explain why social safety, the felt sense of belonging to a group, of being held within a community of people who have your welfare in mind, is one of the most powerful inputs to the nervous system's threat assessment system. The amygdala, evaluating the question of whether it is safe to sleep, is not just listening for physical dangers. It is reading, in part, the social landscape. Are there trusted others near? Is there belonging here? Is there someone who would notice if something happened? When those questions have comfortable answers, the nervous system can ease in a way that goes beyond the rational. Because the answers to those questions mean something that is older than reason. I am not alone in the night. And when those questions have uncomfortable answers, when chronic loneliness, disconnection, or the absence of trusted others characterizes the emotional landscape of a person's life, this registers in the nervous system as a kind of persistent, ambient risk. Not a specific threat, but a background red that the conditions for vulnerability are higher than they might otherwise be. The amygdala does not distinguish, on the most ancient level, between the physical aloneness of sleeping in the open away from the group and the emotional aloneness of feeling unseen and unconnected in the middle of a busy life. The signal it reads in both cases has a similar quality. There is no protective social field here. Stay more alert. This is a compassionate thing to know about loneliness. It is not weakness. It is not a failure to be more self-sufficient. The nervous system's response to feeling alone in the world is a biological response, written into the circuitry by millions of years of evolution that served a genuine purpose. And understanding this can help us take loneliness seriously, not as a character flaw to be overcome, but as a genuine biological need that, when met, allows the nervous system to rest in ways it simply cannot access alone. Let's turn now to something closer to the present moment, to something you can notice in your own body right now, if you are still gently listening. The body, in this quiet, is trying to communicate something to you, not in words, in the language it has always used, the language of sensation, of weight, of warmth, of the quality of your own breath moving through you. There is a region of the brain called the insula, tucked into the fold between the frontal and temporal lobes on each side of the brain. The insula is sometimes called the seat of interoception, the brain's representation of the body's internal state. It is the part of the brain that knows you are thirsty before you consciously think the word thirsty. It is the part that registers hunger and temperature and pain and the subtle shifts of bodily well-being that underlie what we often call gut feelings. And the insula is deeply connected to the emotional processing centers of the brain, including the amygdala. The body's signals, the ones the insula processes, feed into the assessment of safety and threat. When the body is holding tension, when the breathing is shallow, when the heart rate is slightly elevated, the insula registers these states and they contribute to a read of heightened alert. The body's discomfort becomes part of the brain's calculation. But when the body is at ease, when the muscles have released their habitual holdings, when the breathing is slow and full, when the heart is beating at a comfortable, unhurried pace, the insula registers that too. And it feeds that information upward into the threat assessment system as quiet evidence of safety. The body saying, we are okay here. Whatever is happening on the outside, in here we are settling. This is the avenue by which body-based practices, slow breathing, progressive muscle relaxation, gentle attention to physical sensation, reach the nervous system's threat center, not through argument or reassurance or cognitive reframing, through direct biological communication. The body speaking to the brain in the only language the amygdala truly understands, the language of what is actually happening in the physical body, right now, in this moment. And the beautiful thing about this communication pathway is that it works in both directions. The brain can release tension in the body by entering a state of safety, but the body can also lead the brain towards safety by releasing its own tension first. Which pathway you enter from hardly matters. The loop runs in both directions, and you can begin it wherever you have access. Right now, you have access to the body. Notice the weight of your head against whatever is underneath it. That weight is real. It is gravity. It is the earth holding you. Your head does not need to do anything to maintain its position. It can simply rest there, completely supported, completely without effort. Notice your shoulders, and if there is any holding there, any slight lifting, any bracing, see if you can let it go. Not force it, just invite it. Give it permission. The shoulders do not need to be anywhere right now. They can rest against the surface, against the air, against the weight of their own comfortable stillness. Notice your jaw. This is one of the places the body holds its vigilance most persistently. A subtle clenching, a keeping readiness, a tension so habitual it has stopped registering. Let your teeth drift apart slightly. Let the muscles of your jaw soften. And feel as they do how that softening travels into the muscles around your temples, into the space between your eyes, into the back of your neck. The brain is receiving all of this. Every small release, every softening, every downward settling of the body is being read by the insula and carried upward into the amygdala's ongoing calculation. The calculation is updating in real time. The evidence is accumulating. We are safe here. We are comfortable here. We can let go here. Let me tell you about the thalamus, because the thalamus is doing something quite wonderful on your behalf right now, and it deserves to be acknowledged. The thalamus sits roughly in the center of the brain, and it acts as a relay station, a hub through which almost all sensory information passes on its way to the cortex. Sounds that reach your ears pass through the thalamus on the way to the auditory cortex. The visual information from your eyes is relayed through the thalamus to the visual cortex. Touch, the proprioceptive signals from your muscles and joints, nearly all of it routes through this central structure before reaching the higher brain regions that process and interpret it. And during sleep, something remarkable happens in the thalamus. Specialized neurons there begin to generate a particular pattern of electrical activity called sleep spindles. Brief bursts of rhythmic activity in the 12 to 15 Hz range that appear on an EEG as a distinctive spindle-shaped wave and last for about half a second to 2 seconds each. These spindles are generated as the brain transitions from wakefulness into the deeper stages of non-REM sleep, produced by a specific circuit between the thalamus and a surrounding structure called the thalamic reticular nucleus. What sleep spindles do is remarkable in its elegance. They act as a gate. As the spindle activity fires, it temporarily blocks the relay of sensory information through the thalamus to the cortex. It is as though a door closes briefly, rhythmically, between the outside world and your sleeping brain. The sounds of the room are still reaching your ears, but during the spindle, the door is closed, and they do not make it all the way to conscious processing. They do not wake you up. Research has found that people who generate more sleep spindles, whose thalamus produces these gating bursts more frequently and more robustly, sleep more soundly through ambient noise. They are better buffered from disruption. The world can continue its ordinary small sounds around them, and the sleeping brain, behind the rhythmic spindle gates, does not stir. And here is something that connects this directly to everything we have been discussing. the generation of sleep spindles appears to be modulated by the arousal state of the brain. A nervous system that is running high with elevated norepinephrine with an amygdala scanning at high sensitivity generates spindles less consistently. The thalamic gating mechanism is less reliable. The sleeping brain is more easily penetrated by sensory information. The sounds of the night are more likely to reach it, to register, to pull it closer to waking. A nervous system that has settled, that has allowed its arousal chemistry to fall, that has received enough evidence of safety to permit the locus coeruleus to quiet, generates spindles more readily. The gates close more reliably. Sleep is deeper and less easily disturbed. This is yet another way in which the quality of felt safety has direct, measurable consequences for the quality of rest. Not as a metaphor, as neuroscience. The sleeping nervous system that feels safe is physically better insulated from the world. Its thalamic gates close more completely. It is more fully elsewhere. We have been on a long and beautiful journey tonight. We have traveled through the amygdala and the prefrontal cortex, through the parasympathetic nervous system and the vagus nerve, through the polyvagal hierarchy, through the cortisol melatonin dance, through the hippocampus's contextual memories of safety, through the glymphatic tide that washes through your sleeping brain, through the slow waves that restore the clarity of your neural landscape, through adenosine's patient biological argument for rest, through oxytocin's quieting of the alarm, through the ancient evolutionary pull of social safety, through the insula's body-to-brain broadcast of peace, and through the thalamic gates that close around your sleeping mind. And woven through all of it like a single long thread has been one idea, one central, deepening, returning idea, which is this: sleep and the felt safety that makes deep sleep possible are not achievements. They are not things you earn or force or discipline yourself into. They are the natural resting state of a nervous system that has received enough genuine evidence that the world, right now, in this place, at this hour, is trustworthy. And the building of that evidence takes time, takes repetition. It is never completed all at once, but it is always in progress, always ongoing, always being updated by new experience. By tonight's experience, because here you are, in a place that is yours or safe enough to be yours for now, in a darkness that is soft rather than threatening, with a body that has carried you through today and is now asking, in every way a body knows how to ask, for rest. And you are here for it. You are lying still and letting the science find you and letting the chemistry do its work and letting the night be what the night is. That is not nothing. That is everything. I want to say one more thing about the nervous system's capacity for change, because I think it is the most important thing in all of this, and I want it to be the last idea that visits you before the words stop coming. There is a process in neuroscience called long-term potentiation, the cellular mechanism that underlies learning and memory. When two neurons fire together, repeatedly and in close succession, the connection between them strengthens. The synapse becomes more efficient. The signal passes more easily next time. This is the basis of all learning. Patterns that are repeated become more deeply etched into the neural architecture. And what this means for the story we have been telling tonight is this: every single time the nervous system successfully moves from arousal to rest, every time the amygdala is quieted, every time the prefrontal cortex sends its calming signal, every time the vagus nerve fires its long parasympathetic broadcast through the chest and belly, every time the body releases and the brain follows, or the brain releases and the body follows, those neural circuits are being practiced and strengthened. The nervous system that can rest is becoming, through the act of resting, better and better at resting. Not dramatically, not overnight, but incrementally, reliably, in the direction of greater ease. The pathway from arousal to calm, walked often enough, becomes a smoother road. The amygdala, reset enough times by good sleep and genuine safety, recalibrates its threshold over months and years. The prefrontal cortex's calming pathways, exercised regularly, become stronger and faster. The thalamic spindles, generated night after night in a sufficiently settled nervous system, become a more consistent and reliable feature of the sleep architecture. This is what neuroscientists call practice effects, and they apply as fully to the regulation of sleep and safety as to any other learned skill. The nervous system that learns through repeated experience that lying in the dark is safe, that the lights going out does not signal danger but invitation. That nervous system carries that learning forward. It writes it into the structure of its circuits. It expects, with increasing confidence, that what comes after darkness is rest. You are part of that process right now. Tonight is not wasted, whatever happens with the sleep itself. Tonight, your nervous system is receiving information. Your amygdala is noting, with whatever part of it can note things, that the darkness has come and nothing threatening has happened. That the body has lain here and been unharmed. That the quiet has continued. All of that is going somewhere. All of that is being stored, compared against previous nights, integrated into a slowly updating prediction. The prediction is moving very slowly in the direction of safety. Your breathing has changed. It almost always does by this point in the night. It has slowed or deepened, or perhaps you have simply stopped noticing it, which is its own kind of gift. The breath that has found its own rhythm and no longer requires any watching. The sounds of the room, whatever they are, wherever you are tonight, have become familiar rather than new. The brain has cataloged them. The amygdala has assessed them and, finding nothing alarming, has allowed them to fade into the background texture of a quiet night. They are just sounds now. The world going about its ordinary, unhurried business. Your limbs are heavy, not uncomfortably so. Heavy in the way that only deeply resting limbs can be heavy. Heavy with the honest weight of muscles that have worked today and are now being allowed to do nothing at all. And somewhere in the deep architecture of your brain, in those structures we have been visiting together, the amygdala easing, the prefrontal cortex quieting, the locus coeruleus falling toward its nightly silence, the ventrolateral preoptic nucleus beginning to assert its soft authority over the wakefulness systems. Somewhere in all of that, the tipping point is near. The adenosine has been building all day, and it is patient and persuasive, and right now it is at its most eloquent. The melatonin is flowing. The cortisol has fallen. The body temperature has dropped its slight, important degree. The thalamic gates are beginning to flutter, testing their rhythm, preparing to close around your sleeping mind. You have done enough. You have understood enough. You have thought enough and felt enough and been present for enough. The rest of tonight belongs to the brain's own quiet work. The glymphatic tide, moving through. The slow waves, editing and restoring. The hippocampus, replaying and filing. The REM cycles with their low norepinephrine dreaming, processing the emotional textures of the day. All of it will happen without you having to do anything at all. All of it will happen because the nervous system, given the right conditions, simply does what it is designed to do. It rests, it repairs, it learns, prepares. You only need to be here, in this bed, in this body, in this darkness that is safe enough and quiet enough and yours. The brain will take it from here.